The GUI we have created is designed for beginners in structural mechanics. It's a very simple GUI which does a few things. Firstly, it is a GUI that will calculate the bending moment diagram on the top left, the shear force diagram on the top right, and the deflection diagram for a cantilever beam. Now, included in this GUI is a second moment area calculator, which is here, and it is specifically for I-beams and box beams, and I-beams with flange in millimeters of a given value, web, height, and width. And simply to convert this into a box beam, the web must be equal to 0 for a box beam. So the GUI is preloaded with these values and it will tell you if there are any warnings, for example, if the point load application is outside the beam length, for example. Now let us run it with these values. So for a beam of length 10 meters and Young's modulus in gigapascals of 200, so in this case steel, a second moment area of this value in millimeters to the power 4. However, this can be changed to either centimeters or meters. The UDL properties can also be changed, so the length of the UDL from the support and its value in kilonewton meters. The point load properties can also be changed, so the application of the point load from the support, so 0, 0, and the point load value. I will show you here that the point load is designated with an arrow. In fact, if we change the point load position, let's make it 2, we can see that the point load has been moved and the bending moment diagram in blue has changed. We can also change the value of the UDL. So let's make the UDL, for example, 4 meters long from point 0, 0 with a value of 10. You can see here that the UDL is shown in red and the bending moment behind it. This GUI also allows you to interactively see different values on the graph. So if we are interested in the highest, we can see that at x equals 0, so the support, the bending moment is 90 kilonewton meters. On the top right, we can also see the shear force diagram, where this little kink in the value is caused by the point load application at a distance 2 meters. Underneath we can also see the deflection in meters, and in this case obviously it is a bit too much for this beam because obviously the beam properties are slightly off, but we can make it a more realistic beam by changing these properties. Also, part of this GUI is a second moment area calculator. Now this calculator isn't directly related to the second moment area value here. This is because it can be used separately. So students practicing both analysis of cantilevers or calculating second moment areas of actual beams can use this GUI in different ways. So we can put an example here, and we can say a flange width of 30, a web of 20, a height of 200. And we can see here the beam has changed and the second moment area also in millimeters to the power 4. Now this can also be changed into a box beam by applying the fact that the web must equal to 0. So the box beam has a flange, in this case, and web of 30 and a height of 200 with a width of 200. Now to check if this warning box is correct or not, we can also test it out. So let's try and put the UDL further along the beam than the beam is long. So let's try and put that at 15. So let's take an example that the UDL is actually longer than the beam is long. In this case the beam is 10 meters long. Let us try put a value of 15. As you can see, the warning box says the UDL is outside beam length. Now we can try the same for a point load, and we can apply a point load at 11 meters and the point load is outside the beam length. Now I will also take you through the code behind this GUI. So if we close this interface and we go to the main block of code, under each function, I set it to update axis handles. An update axis handle is a function right at the end of the GUI code, as you can see here. So the function starts with clear all axis. I then set axis handles axis 7, which is the axis where the image you see of UCL engineering is located. The following piece of code extracts each value from the text box in the GUI. So each text box would be filled with a string. So what I say here, for example, is to get from the handles, which is the little text box for the beam length. In fact, I will show you here if I can just run it. So in this case, value beam length is this text box here. So I say to extract from it the string inside this box. But as a string, this value is insignificant. I need it as a number. Therefore, I use the string to double command, which converts the string in beam length to the number. This is repeated for the Young's modulus, multiplied by a factor of 1 to the power 9 because it is a gigapascals, and the second moment area, UDL length, UDL size, point load application, and point load size. For this section here of second moment area, there is a slight change. Since we had decided to put a pop-up menu, 3 choices can be made in millimeters, centimeters, or meters to the power 4. So the first value would be 1, 2, and 3. I therefore say that when taking the values from that text box, converting it into numbers, I also say that if that second moment area units of the pop-up menu is position 1, then the second moment area should be divided by a certain number. If it is 2, it is divided by another number to equalize all the units into meters, which we are using in the calculations further on. This is the set of code that shows up in the warning dialog box when the point load application is greater than the beam length or the UDL application is greater than the beam length. The main set of calculations is done in the following section. We set the beam x values from 0 in intervals increasing of 0.01 until the beam length. We also set a line of x times 0, which is the unloaded beam. And the following section, we insert a step value of n equals 1, and as you can see at the end of the loop, n increases by 1 every time. And we use the principle of superpositioning and find the moment, shear force, and deflection of each point, bending moment, shear force, and deflection of the point load and the UDL effects separately. So these are the simple equations that can be derived mathematically, and obviously considering a point load alone, once the I value is past the point load application, there would be no bending moment and no shear force. That is why this is 0. This is repeated for the UDL as well. At the bottom here, the bending moment, shear force, and deflection are recorded into a matrix with a position of value n. Now the value n changes at every iteration of the loop. The remaining parts are simply of plotting the graphs on the GUI. So as you can see, to plot the bending moment diagram, I have the handles on the graph BM, and this is simply plotting the area of the bending moment and the colors of the lines, etc. The part here is to plot the point load arrow and the UDL area you see. The section underneath is similar to the bending moment section, where I take the handles of the graph of the shear force and I simply plot the shear force diagram. This is also repeated for the diagram of the deflection. This is the new section, which takes into account the second moment area calculator. Now I do a similar procedure to what I did before, so extracting all the values from the text box and converting them to a double, and then simply deciding that if the, in this case, web thickness is not 0, you will calculate a second moment area for an I-beam, while if the web thickness is 0, it calculates and plots the diagram for a box beam. And that is the GUI code of the GUI for a small cantilever and a second moment area calculator.